In this video, we're going to look at a very, very important topic in algebra, factoring. Factoring comes up all the time in algebra and is useful for solving all types of problems. So it's a skill that takes a lot to develop, but it is super important that you develop it and become good at factoring because it is at the foundation of solving so many problems in algebra going forward. So this term factoring, what is it? Well, I can define factoring a polynomial means expressing a polynomial as a product of monomial and polynomial factors. All right, so you break a polynomial up into things that multiply back to it. Let's think about a number first of all. If I say factor 12, well, that would mean that 12, I'm going to break it down into numbers that multiply to 12. Prime numbers that multiply to 12. Remember the word prime factorization? So 12 is 2 times 2 times 3. I can say there that I factored 12. I broke 12 down into numbers that multiply back to 12. Now when we do this with polynomials, it's going to look a little different. And the way we're going to first talk about it is factoring out a greatest common factor, which is essentially doing the distributive property in reverse. So let's think about this. If I do the distributive property on this, 3x times x plus 2, I would get 3x squared plus 6x. And that's the distributive property. But factoring is going to go backwards. Suppose I have the equation 3x squared plus 6x, and I say factor that. The end result would be 3x times x plus 2. That would be the factorization, or the factors of 3x squared plus 6x, because I have taken this polynomial and broken it down into things that multiply back to it. And I've broken it down as far as it can. I can't split apart either of these factors any further. All right, so let's do some examples and see how this works out. Factor 27x plus 18. And we are going to do what I call factor out the greatest common factor. So factor out the GCF. And to do that, you are looking for the largest number that divides both terms here, or all the terms in the polynomial, and you're going to factor that out. And to do that, that'll be a skill we'll learn and get better at, but the first time we do this, let's take it slow. So 27x, I'm going to break that down into its factors. 3 times 3 times 3, that's 27 times x. So I pulled that apart as far as I can as far as just the numbers. And again, this is the long way, but I want to show what's happening. So it's that plus 18, which that as its prime factorization is 3 times 3 times 2. Now as far as the factors I have here, what is the greatest common factor between the two? What are all the numbers, all the factors that both of these terms have in common? I have 1, 3 here, 1, 3 here. I have 1, 3 here, I have 1, 3 here. So I can factor out a 3 times 3 out of this. So it ends up with 3 times 3. And if I take that out, what am I left with? 3x, and then a plus 2 is left over. See, I've got this 3x left over, and this 2. And then simplify that. 3 times 3 is 9, times 3x plus 2. So I have factored 27x plus 18 by factoring out the greatest common factor of 9. That's my GCF right there, 9. Greatest common factor between the two terms of 27x and 18. And you can always check your factoring by going in reverse. If I distribute this 9 in, I should return right back to 27x plus 18. So what do we got? 9 times 3x is 27x plus 9 times 2, which is 18. Boom, it's where I started. So that means I am correct. So once again, the factorization of 27x plus 8 is 9 times 3x plus 2. Let's try it again. the long way again. So I'm going to break down each of these terms into the basic numbers that factor each. So 15x, well that's 3 times 5 times x, plus 25x squared, which is 5 times 5 times x times x. What is the greatest factors in common between these two? Got a 5 and a 5 and an x and an x. So I can factor out a 5 times x, and what am I left with? I'm left with a 3 right there, and then a 5 and an x over here. So I've got 3 plus 5x left over. So I was able to factor out a 5x, and I'm left with a 3 plus 5x, and there's my factorization. If I go backwards, do I get the same thing? 5x times 3, 15x, plus 5x times 5x, that's 25x squared. Sweet. So I'm correct, because when I went backwards, I returned to where I started. So I factored 15x plus 25x squared because I broke it down into terms that multiply back to my polynomial. Okay, what if I have 32x plus 16, and I say factor that. So let's try and do this a little bit faster now. I'm thinking, what's the largest number that divides 32x and 16? And that largest number, in quotes, because that could involve x, it could involve an x squared, it could involve a variable. It's a lot like reducing fractions when you think about it this way. If I'm reducing the fraction 12 over 4, well, that reduces to 3 over 1. Right? Because you are thinking, what's the largest number that divides both 12 and 4? And you divide both of them by that. So the largest number here is 4. So I go 12 divided by 4, 4 divided by 4, and I'm left with 3 over 1, or 3. So in this case, that largest number is what you're going to factor out of your polynomial, and then you write what's left over. So what is the largest number between 32x and 16 that you can factor out? 16. And if I take out a 16 out of 32, so if I factor out a 16, I'm basically saying, what is 32 divided by 16? It's 2. So I'm left with a 2, and then the x was unaffected there. If I factor out a 16 out of 16, what am I left with? Well, I can think, what is 16 divided by 16? It's 1. So I'm left with a 1 there, and factored is 16 times 2x plus 1. I am able to factor out a greatest common factor out of as many terms as I want. So if I have a trinomial here, I can factor out a greatest common factor out of all of it. And that is, whatever I factor out has to be in common between all 3 terms. Well, it looks tempting to factor out a 7 because it's in common of those two, but notice there's no factor of 7 there in the third term. So if I were to factor out a 7, well, I couldn't do that because it's not in common between all 3 terms. What is in common? Well, there's an x here and an x here and an x here. So how many x's can I factor out? Well, again, let's think wrongly. If I were to say, well, let's factor out an x cubed. So do I have an x cubed in each of my terms? No, I don't, because here I only have an x squared. I have 2 x's. I need 3 of them to be able to factor out all 3. So I can't do that. I can't even do x squared. I can't factor out squared because even though I'm good here, I only have 1 x here. So what is the greatest thing I can factor out of this? Just 1 x. And if I factor out 1 x from each of these terms, I'm left with a 7x squared here. See, I took away one of those x's, so it's down to squared. Plus 14x here. I took away 1 x, so the x squared goes down to just x. And I'm left with minus 1 here. Let's break that one down. So negative x, well, that's equal to negative 1 times x, right? There's the implied 1 there. If I factor out that x, if I pull that away, what's left over? Just a negative 1. So that's why I have negative 1 at the end. And here is my factored polynomial. Let me do one more really quickly for you. See if you're getting a hang of it. See if you can do this before me. I have the polynomial 2x to the 4th plus 4x cubed minus 6x squared. I'm looking at this. What is the greatest common factor between all three terms? I notice I can factor out a 2 from it. That's the greatest number. And then I can factor out an x squared. There is an x squared in each of those terms. That's the greatest amount of x's I can pull out. So I'm left with 2x squared as the greatest common factor. And when I factor that out, in the first term, I'm left with x squared. In the next one, I'm left with 2x. And in the last, minus 3. I went quickly over that, and I want to see if you were able to do that first. And if not, can you take a look back through that and see how I factored that out?